Battery innovation is facing a bottleneck. We need lighter, longer-lasting, higher energy density batteries for electric vehicles, for stabilizing the grid, for powering robots, and even for lifting the next generation of aircraft. The current pace of battery innovation isn't enough. The problem lies in the scale and complexity of the design space, or parameter space, we're dealing with. A typical battery has 6 main components: a cathode, an anode, a separator, electrolyte, and 2 current collectors. Each of these can be made from thousands of materials and processed in different ways. The combinations of these materials quickly multiply into millions, if not billions. Moreover, different applications require different material combinations. A battery for an EV needs to be lightweight and charge fast. A battery for grid storage should be cost-efficient, but weight isn't the biggest issue. These trade-offs mean that different applications require different design criteria. Then there are the charging and discharging protocols. These are made up of steps, each controlled by either constant current or constant voltage. Small changes at each step can lead to big differences in durability and performance. So the space of possible protocols is also massive. The main challenge is how to efficiently search through this enormous design space. That's where AI comes in. Tools like Bayesian optimization, strictly speaking not an AI algorithm, but often used in AI pipelines, help explore large parameter spaces efficiently. They don't guarantee the perfect answer, but they're good at narrowing down the best candidates quickly. AI is also good at finding patterns in large, complex datasets. Battery behavior isn't just a function of individual materials or steps, it's the result of interactions between dozens of variables. Machine learning models can spot relationships that are impossible for humans to discover. In practice, AI is already being used in battery innovation, but mostly in research labs. One aspect is high-throughput material discovery. Instead of making and testing thousands of materials in the lab, researchers simulate materials computationally based on first-principle models and use machine learning models to predict promising candidates. This speeds up the early screening process significantly. In the real physical world, AI has been applied in predicting battery cycle life and optimizing charging protocols. These are both critical for improving performance and reliability without changing the physical design. We've explored some of the most important breakthroughs in these domains in earlier videos, with a focus on work from William Chui's research group. But there's a major bottleneck. AI is extremely data-hungry, and battery data is very expensive to obtain. Experimental data is expensive and slow to generate. Testing a single battery over its full life takes days or even weeks. The data is also subject to testing and sample variations. The same battery at different locations and tested with different equipment will result in different measurements. Moreover, manufacturers often protect their data, and academic labs typically work on small, incompatible datasets. Computational data is also expensive. Simulations require a lot of time and computing power, and while some datasets are public, they're not always large or diverse enough to train useful models. So, despite AI's potential, the lack of quality data is holding the field back. Moreover, simulated results need to be tested in the real world to be useful, and that handoff is often slow and fragmented. Autonomous robotics could help close this gap by running fast, repeatable physical tests that keep pace with computational outputs. To break through these bottlenecks, researchers from institutions and corporations have proposed a centralized infrastructure for data collection and sharing. This involves standard protocols for testing, so results from different labs can be compared and combined. It also means establishing centralized robotic testing facilities that can generate large, consistent datasets automatically. If we want AI to help drive battery innovation at scale, we first need to solve the data problem. But the real question is, who will fund these testing facilities? And will major battery suppliers be willing to give up some of their data advantage in exchange for faster progress across the entire field? Now that you've made it to the end, here are the key takeaways we want to leave you with. Clear and simple. Battery innovation is limited by a massive design space. AI helps navigate it efficiently. But AI is data thirsty, and battery data is fragmented, expensive, and hard to access. Without shared infrastructure and coordinated effort, the pace of progress will stay slow. Key citations that contributed to the production of this video are listed in the description section.